Okay, so I'm going to talk a little bit about measurements and models. That's kind of what we do. And I guess it's a PA forum, but I got at least one or two slides on LNA applications. So this is the agenda. Give you a brief introduction, summary of Modelithics, and make the point that excellent circuit models start in the lab, at least measurement-based circuit models, which is primarily what we do. We also develop EM analysis-based models, so we call them 3D EM models, but that's not the subject of our talk today. And we have a product called the Modelithics Complete Library. I'll tell you a little bit about that. And that was really something that has been our primary vehicle for distributing these excellent models that we develop from measurements. And we'll talk about transistor models and then summarize, okay? So we started in 2001, and what's different about us is that we focus entirely on measurements and models, and we're really the first independent company that has addressed models that are standardized across various vendors, supporting multiple simulators. And since it's what we do, every model comes with a model data sheet that tells you about the test fixtures used for the measurements, the measurement validations, reference planes, all the details that you might need to know as a designer about where is this model's kind of sweet spot, where is it good, where has it been validated, and so on, and maybe some examples of validation and so on. Another thing that's different is that, say for passive components, the world, if you will, without Modelithics is a world where you go to many different vendors' websites and you can get an S parameter file. The S parameter file is valid basically on the test fixture, substrate, and solder pad footprint that it was used to make the measurement. So it's really just a snapshot. And in contrast, our models are scalable in terms of the substrate, solder pad dimensions, and part values, so you can optimize and tune them, take into account the circuit environment that you want to work in. And of course, you could develop these models yourself, but if you're a circuit designer, that's kind of a distraction from your design flow process. And I always remember one of our customers that says, well, so the way you would make the measurements for your models is the way I would do it. So I would rather just go ahead and use your models and only pick models that are in your library and then focus my time on circuit design. So our primary offering is we sell and support libraries and models that plug and play into, today we're talking about AWR, Microwave Office, AWR Design Environment. And today it represents more than 16,000 commercial off-the-shelf components for active and passives. We also perform custom measurement and modeling services, and then we work with vendors, suppliers through our vendor partner program. So the slide here on the right just shows kind of I call it kind of our IP story, because for us, every model for a commercial part is intellectual property that we package up into our libraries. And so today we have our models organized into 630 different models that represent, as I said before, over 16,000 parts. And how does that translate? Because a model for a passive, one capacitor model might represent 100 parts. Now, some of our resistor models represent 1,000 resistor values and so on, because you can scale and use optimization, tuning, and statistics. So just some recent lab enhancements. I said, we focus a lot on the lab. So first of all, we're measurement experts, and then we're modeling experts after that. So we recently added the AMCAD pulsed IV system and software to our system, and we also invested in a full temperature scalable cascade probe station. We have many probe stations. We like probing. We probe RFPC boards, we probe wafers, and the only reason we don't probe is when the power doesn't let us, and then we go to coaxial fixtures when we have to, and even waveguide in some cases, high frequency and so on. So our complete library is kind of broken down into different categories. The CLR is scalable models we call global models for RLC components, and then we have nonlinear models for transistors and diodes. Some of these also have substrate scalable properties, and again, each model's capabilities are represented in a model data sheet. And then the system level component library is kind of a bucket that contains higher level component models for things like filters, amplifiers, mixers, couplers, diplexers, things like that. And we also have a substrate library that consists of many popular substrates predefined, M sub statements, And the parameters there are derived from our own measurements. So when we do TRL calibrated measurements, we backfit the dielectric constant that works well. And so they're just recommended values that we found work really well for a wide range of substrates. And there's an S-power library, which is S-parameter models that haven't been reduced to scalable equivalent circuits. And so there might be some parts there that we don't have represented in scalable models, but they're also in, they're S-parameter models, so they often might represent also a whole family, but might be part value selectable. So they're not just S-parameter files. And many example projects. So when you install our complete library into NI AWR, you will find, under the X libraries, this is our version 18.1, and so the models are either organized by type here, and you can see amplifiers, attenuators, capacitors, all the way on down, transistors, and so on, or by the vendor. And when we organize by the vendor, then you would break out and see there's something like 65 or more vendors that are represented in our libraries, and each one of them you can push in and see what we have for those vendors. We've been at this a while, so we got a lot of really good models. As I mentioned, one of the main things is the substrate and part value scaling. So this is just showing a single part value of a capacitor on 3 different boards. At low frequency, say below 500 megahertz or below a gigahertz, all of the data kind of lines up. But then when you go above that, and that's why I always tell people, if you're using surface mount components above a gigahertz, you really should take a look at our models. And the blue is measurements and the red is model, again on 3 boards. This one is like something like probably an 8 mil Rogers out here, and this one's probably a 60 mil board. Just demonstrating part value scaling. This is scaling the part value for an inductor and a capacitor. Here we have both amplitude on the left and phase on the right, and here is just amplitude of S11 for a part value sweep of a capacitor. Active models, this is just a diode showing temperature scaling. The symbols are measurement data at 3 different temperatures, and that's a Schottky diode. 25, 53, and 85C. And this is just a snapshot of a MOSFET model, S parameters on a 10 mil Rogers, and on this 60 mil Rogers board. Yeah. Okay, thanks. All right. So one of the new features. So with each new release, and we do at least one major release every year, and with each new release, we introduce new features too. And some of the things that we have are dynamic layouts that we've extended to our diodes library. We before had, so dynamic layouts means that as you scale the pad dimensions in the simulator, it will adjust not only the electrical model but also the layout model, and that's one thing. And then we have an obsolete model tree, so we never actually remove a model from our library. So sometimes a vendor will come along and say, hey, we lost a lawsuit, you have to take that, that happens. You have to take that part out of our library, and we don't. What we do is we'll put it in a hidden palette, or they'll say, look, we're not offering that part anymore, it's obsoleted, and we have a new replacement part. So on the data sheet for that part, so if you had an old design, what we don't want to do is have you pull up a design you did 5 years ago and have it not work. So if you install our new libraries, the model will be there, it'll show up in your design if you have it, but it won't be in the new library tree. And then this is kind of a new feature, which is, I think Yvonne will like this one, but a lot of people, PA designers, want to put parts right on a microstrip line. Our standard model comes with basically reference planes that include our pad edges, so we include a pad in our basic model. And if you want to mount it on a microstrip line, I'll show you an example of a design that Yvonne did that he used his know-how to put in some negative transmission lines to adjust for the fact that I kind of have a negative pad here. The reference plane is actually back here somewhere. So this is a design that we presented a couple years ago at this conference, and it's been in an app note and so on. And again, Yvonne likes to use these parts right on the microstrip line and not have a pad. So what he had done in that simulation, which got really good results, but he had a negative transmission line to adjust for the reference planes of these pads. So with the new models, you don't have to do that anymore. So I kind of got those out of there, and we just put in the new shunt mode model. It's like on a pull-down menu. And this is showing the red. It's really kind of hard to see. The pink is the measured data. This is just S21 of the amplifier, right? This is what happens if you didn't do that negative transmission line correction. You get this for the sweep of the S21, right? But the red and these two curves right here that line up, it's really hard to see the difference. There's actually two curves here. One is Yvonne's tricks, and the other one is the new model. So you don't have to be so much of a guru to figure out how to sort of fudge the pad model. It's now correct. So when you put that part on the line now, you just select that feature, and it'll give you the correct result. So other things we do with every new release is we add models. And the models that get added, people ask us, how do you choose which models that you add? I always talk about being the golden rule. Whoever buys the gold gets to set the rules for what models we add in general. We do have a running wish list. So as a company has matured, and we're in our 18th year now, we do invest in our own internal research into developing new models that are on a wish list. So if you're a customer of ours and you want to see models added, we always want to hear about it. It's just we have to do those in between funded projects. And the funded projects from either vendors, or these are vendor partners, from vendors or from designers, those ones are going to get the priority. So we had 47 new models in AWR for a whole range of component types, as you see here, both active and passive. So that's always, I think one of the things that our customers really like is that we're not just standing still, we're developing models all the time. This is an example of I did say I was going to do at least some attention to low noise. It's actually a pretty popular part from CEL, and this is a low noise p-hemp model. It's both, it's nonlinear. You can see over here we've got comparison, the nonlinear model to fundamental third, fifth, and seven harmonic behavior. Here's noise NF min. Again, it's a very low noise part. 8 gigahertz, we got a half a dB noise figure here. And, it's a nonlinear model, but it also is predicting noise. And this is what it looks like in AWR. Let's see, and we always tell you what this is just a snapshot of the model data sheet. We always tell you what it is. This one model is validated at 30 gigahertz. Inside is the EE-hemp model, and so on. This is another example of an S parameter model that we have for an amplifier. So this is a Gorilla RF amplifier model, and so it's validated to, this is just up to 8 gigahertz, single substrate. We tell you what the substrate is, the voltage, and things like that. So that model is going to predict S parameters and noise parameters in that case. So that's in the library. These are what the parameters look like. We had another a newer one that's out to 40 gigahertz. So this is a 40 gigahertz model, S parameter data that was used to generate the model. So we have, let's see, this is noise parameters over here and S parameters over here. So we have a nice 50 gigahertz noise parameter capability. This is an example of a relationship we have with one of our vendor partners, which is a little bit unique. So this is Corvo, and we have been working with them for over 4 years, and we have now a standalone library that's free to designers, and it represents more than 70 high-power GaN die and package device models, and we're adding models, we're developing models on a continuous basis. And so we have what we're providing for the customers is quality installer, user manual, very easy to use. It's really a PDK for discrete power transistors. Let me just ask if how many in here have actually used this library? Okay. Dominic, you have as well? Yeah, thanks. Yeah. Okay, and we have a lot of features. Now the model we use for this is a Modelithics customized version of the Angelov model, and it has features like, in some cases, scaling of the operating voltage, VDSQ, ambient temperature, self-heating effects, and intrinsic voltage current sensing. Sometimes there's a switch to turn it on and off bond wires if they were part of the test fixture, and some of the models have noise modeling and channel temperature sensing. Okay, the best part for designers is that it's free, and it's now in use by over 225 organizations worldwide, so it's pretty popular. This is just an example of what the palette looks like. There's die. We have some that are just small signal noise models and packages. So these die and package models are nonlinear models. This is just a palette of die models for what is their GAN 15 process. So these are die. This is just a simulation of intrinsic waveforms. So a lot of PA designers want to use Waveform Engineering. And so recently I've been asked to author or co-author a blog series. There's like, I just finished a third blog for Corvo on, the basics of understanding waveforms and waveform engineering. But it's really key to be able to provide access to the intrinsic waveforms inside of the transistor, inside of the parasitics. And this is just what it looks like in terms of the die models. No, these are package models, package models. Okay. And there's an intrinsic waveform demo here. And I guess I don't have time to really do the demo, but it just shows optimizing a class F where the AWR schematic here is set up to use a harmonic tuner, and you can tune the third harmonic amplitude and phase to optimize. And if you look at power and efficiency in the example that I showed, went from about 70% efficiency to 80% efficiency. So about 9 or 10 points were gained just by optimizing that third harmonic and squaring out the voltage waveform. And that's what we're showing here. There's 71.5% to 80.6%. So about 9 points of efficiency improvement. So two libraries that work really well is our complete library along with our Corvo GAN library. And that's some of the examples that Yvonne has done and Dominic have used those combinations. And we encourage you to give it a try if you haven't done so. Here's a customer, a story from a happy customer, right? So don't take it from me, take it from our customer. This is, and some of you might have seen this because it was an NI AWR success story. But it was also a two-part article in HFE Design Magazine, and it was in August of 2017 was part one, and part two was September. And they should say September. So the first part was a filter design, and the second part was a power amplifier, and this was all part of a transmitter. So the filter was needed for harmonic suppression of the PA, and the PA was a two-stage design using one of the Corvo GAN models. And it was an interesting story because he actually used the model a little away from the optimal point of voltage and so on, but it worked out well. This is showing just the filter, kind of an ideal simulation and non-ideal simulation using the full parasitic models. And it was really important to him to be able to reject harmonics out in here, so he had to fix this, which he did by adding another filter, which was a radial stub filter on the output of his lumped element filter, and this was his final kind of measured and simulated result. This was his design. He built it once and basically built it and shipped it, including the PA. So this was the filter part of it, and his PA was a two-stage PA. This was Quasonics. So it's two-stage PA, and this is the frequency range, 2.2 to 2400. Not a real high power one, minimum of a watt, but what was really important for him was the maximum current, and he was operating at a low voltage, 12 volts. We actually extracted the model at 32 volts, but it actually worked. It worked out well for him and gave a good result at 12 volts. Some of our models, again, we'll develop them specifically to scale from, say, 12 to 48 volts or something like that. This one wasn't done that way, but it still worked out well. I guess we got lucky a little bit, but no, I mean, we really try to do a good job with the overall extraction of the models. So this is what his overall topology looked like. And there's his schematic. He used some Modelithics here. You can see our passive models are used here, and the active model was used in both of his stages. So he used Waveform Engineering to look at the waveforms, or the intrinsic waveform feature, and then this was his power drive ups, looking at his gain and efficiency. And this is the measured result. So the measurement is P out is this. This is measured and modeled P out, and this is his current. And it was really important for him to stay under 350, I think. And then this is the efficiency here, which is about 50%, a little less than that. So what I tried to kind of emphasize is that good models start in the lab, and I guess what we try to do is provide models that are really easy to plug and play and optimize for your designs, that have good validations. And we, if you need us, we're here. If you need something done on a custom basis, and we can format them so that they're ready to go in AWR. And the Corvo GAN library is a good example of how we're partnering with vendors, and we're very flexible to customize a vendor relationship to work for them and hopefully work for their customers, the designers. So I didn't get the 5-minute warning, so.
We've got questions on.
Okay, it's good. So thank you.